Assalamu alaikum, and welcomes to this introduction to graphs in data structures and algorithms. Today, we'll explore what graphs are and why they are such a powerful tool for representing connections. Graphs provide an introduction to handling relationships in a flexible way. Let's begin by understanding the core idea behind graphs. Consider the railway network in Pakistan. Here, the key elements are stations, such as Karachi, Hyderabad, Rodi, Sakkar, Multan, Lahore, Rawalpindi, and Peshawar, with connections formed by railway tracks linking them. For example, the main route running from Karachi through Hyderabad to Multan, then onward to Lahore, Rawalpindi, and finally Peshawar. You can also think of a social network where people are the main elements, connected through friendships or follows that link them in various ways. Or you may consider university course prerequisites with courses like CS 110 connected to CS 112 as a follow-on requirement, or CS 250 linked to CS 212, Math 222 depending on Math 101, Math 234, tied to previous math courses and others as well. These examples all share a commonality. They involve many connections between pairs of items. So, how can these be implemented in a program? Using a list? But lists are linear, making it hard to represent branching or multiple links efficiently. How about using a tree? Now, trees enforce a strict hierarchy without cycles, limiting their ability to handle loops or complex interconnections. Therefore, we need a new data structure that can represent multiple, complex, and possibly cyclic relationships. A graph is such a data structure which is used to represent a set of objects and the connections between them. Formally, G is equal to V, E, where V is the vertex set and E is the edge set. Now, V contains the objects called the vertices, and E contains the connections. These are called edges. Now, this definition provides a foundation for modeling diverse scenarios. Now, use graphs when relationships don't fit a strict hierarchy. There can be multiple connections between objects. Paths can form cycles, like returning to the starting point. And you need to analyze routes, connectivity, and relationships. These features make graphs suitable for complex setups. Now, let's discuss directed graphs or digraphs. Here, edges have directions, like the Twitter follow relationship, where one user follows another without reciprocity. This allows modeling asymmetric connections. Graphs can also be connected or disconnected. A connected graph has a path between every pair of vertices. A disconnected graph has isolated vertices or separate groups. Then a subgraph, which is a smaller graph from a subset of vertices and edges of a larger graph. It maintains connections exactly as in the original. For example, picking part of a railway network for local route analysis. A simple path has no repeated vertices, like DBAC. A cycle, on the other hand, starts and ends at the same vertex without repeating others, like CBAC. Trees can have no cycles. Graphs can. Then a directed acyclic graph, which is a very important concept. Now, this is a directed graph which has no cycles. It is used for dependencies like your course prerequisites or job scheduling. Additional examples or additional types of graphs could be a complete graph, where every vertex is connected to every other vertex. A bipartite graph, which splits vertices into two groups with edges only across the groups. Sparse graphs have few edges. Dense have many. Thank you for joining this introduction to graphs. We have covered real-world examples, definitions, usage, types, connectivity, subgraphs, paths, cycles, and variations. This equips you for further exploration in data structures and algorithms. Thank you.